Okay, so in the last class I described the various processes which occur in neutrino interactions. First, we broadly classified them as charge current and neutral current. Here the neutrino in the initial state but in the final state we find a charged lepton. If it is a neutrino, I find a negative charge lepton. Anti-neutrino, I find a positive charge lepton. Whereas in the case of neutral current process, the neutrino remains a neutrino and anti-neutrino remains anti-neutrino. That's a broad classification. And within each we have quasi-elastic, which means two-particle final state, and here it is elastic. Here it is elastic because the initial state particles are exactly same as final state particles, whereas here, because of the charge exchange, the initial state particles are not, the final state particles are not same as initial state particles, but on the other hand you have a lepton and a baryon, so to speak. So in that sense this is called quasi-elastic. And the second is called resonance in both cases. So here the neutrino gives up enough energy to the nucleon such that a resonance is excited, and the resonance decays into a proton and a neutron and a meson. And so this is characterized by meson/mesons, and they are mostly pions. And for example, if you look at nuance, they list some 98 resonances, 98 resonance scattering processes. But if you simulate atmospheric neutrino events or any neutrino interaction events with the nuance, you will find that in 90% of the cases the resonance events contain a pion. Just a minute, let me put this on silent. Yeah. Same.
Baryons don't come?
No, baryons are there, but usually the baryon energy is so low that you don't detect them. So what I'm saying here is, let's say I have a mu interacting with a proton, and this will lead to mu minus plus a delta plus plus resonance, and the delta plus plus resonance will then decay into a proton and a pi plus. So there is a baryon, but in a typical experiment, this proton energy is low, so low that you don't see the proton, you see only the muon and pi. But we believe in baryon number conservation, so baryon is there. Yeah, and third and most and similarly here also. So deep inelastic scattering is characterized by a multi-hadron final state. Same here also. So here we have these three types of interactions, and obviously the way I have characterized the interactions, you can immediately see that energy plays an important role in which interaction is more important, because this is the simplest interaction with a two-particle final state, which means all that needs to happen is some exchange of energy momentum between the two interacting particles, and this is most likely at low energies, because here I need to produce an extra pion, and to produce an extra pion I need my initial neutrino should have enough energy momentum to produce that pion. So as a rule of thumb, we say that this is dominant at energies less than, one can question this number, instead of 0.5 you may say 0.3, but I have put 0.5, and okay, maybe I'll put 0.3, and these resonance are most important between 0.3 to 1 GeV, whereas deep inelastic scattering is most important when the energy of the neutrino is greater than 1 GeV. So depending on the energy of your neutrino beam, you concentrate on which of these reactions that you need to worry about. By the way, all this based on the energies that I have written down, you notice that all this discussion is applicable only to accelerator neutrinos. If you are talking about reactor neutrinos or solar neutrinos, reactor neutrinos have energies less than 10 MeV. Solar neutrinos have energies less than 15 MeV. And one topic which is of lot of active research are supernova neutrinos. They have energies less than about 30 MeV or so. So, in all these cases, you need to only essentially worry about only the first reaction, the quasi-elastic scattering. You don't have to worry about any of the others. Now, what we want to do is to we want to calculate the cross sections for these reactions. How do we do so? Well, by the way, I said accelerator neutrinos, but I should have corrected. These considerations are valid for accelerator neutrinos and atmospheric neutrinos, that is neutrinos with energies greater than 100 MeV. Atmospheric neutrinos have neutrinos greater than 100 MeV going up to tens of GeV, and there also these considerations are important. How do we calculate the cross sections for these reactions? Well, you can say, okay, I have electroweak model which is supposed to describe all the known things, so I will use electroweak model. Answer is yes, but there are issues involved, and those are the issues that we will discuss. First, to calculate the quasi-elastic cross sections, that is actually quite straightforward. In fact, we go back to Fermi theory of beta decay. Okay, we don't quite go back to Fermi theory of beta decay. We have to worry about the parity violation, etc. So we look at the so-called V minus A Hamiltonian. So we take the weak Hamiltonian to be GF by root 2 psi bar L gamma alpha 1 minus gamma 5 sin L psi bar P gamma alpha 1 minus gamma 5. So where did this Hamiltonian come from? It was written down so that it can describe beta decay and the interactions of muons with nuclei, etc. So, and this Hamiltonian works very well. So we use this Hamiltonian and do the standard particle physics calculation to calculate the quasi-elastic event rates. The corresponding neutral current Hamiltonian actually is more tricky. I will not talk about it right now. We will talk about it a bit later. But I'll talk about it a bit later, but here I'll sort of wave my hands a little bit and say that based on electroweak theory, I can get the corresponding elastic, the Hamiltonian for the elastic process. So the HV or the neutral current process, it will be GF, I will just write GF times psi bar nu L gamma in electroweak model. Neutrinos are purely left-handed, so the neutrino current will have the V minus A structure, but there will be two terms. There will be psi bar P gamma alpha G vector P minus G axial vector P psi P plus psi bar n gamma alpha g vector neutron minus g vector axial vector neutron psi n. Oh, sorry, I missed something. Times psi bar p gamma alpha g vector p minus g axial vector p gamma phi. I forgot to write the gamma phi. Psi bar n g vector neutron minus g axial vector neutron gamma phi psi.
So this gamma alpha, this alpha.
Oh, again, I made a mistake here. Psi bar n gamma alpha. Yeah. Oh, gamma alpha in the subscript. Yeah. Sorry.
What is the difference between subscript and superscript?
As far as we are concerned, there is not much difference. The trouble is we have this Minkowski metric which we need to use. So, what is the difference between P alpha and P alpha? So, this is, if we write this as energy momentum, this is energy. So, if I define what gamma alphas are, automatically the gamma subscripts are defined. So, but in almost all cases, we are not explicitly worried about, wherever we don't measure any polarizations or spins, we don't need to worry about what those gamma matrices are, because we are summing over all the spins. When we sum over all the spins, the gamma matrices get summed over and we get the metric tensor. And metric tensor we know has the form 1 minus 1 minus 1 minus 1. It is only when you are measuring a polarization or a spin that the explicit form of gamma matrix is important. And in such a situation, you define what the gamma upper index is, and once you define what gamma upper index is, then the gamma lower index is automatically defined.
I don't understand why in the top equation, in the lepton neutrino portion, the gamma alpha is superscript.
Okay.
But for the proton neutron side.
Okay. I have to use some convention. So I use the convention that I will put the upper index for the leptons and lower index for the proton. But if I write this, that is equally correct. So whenever there is a dot product, suppose I have two momenta P and Q. P alpha Q alpha is same as P alpha Q alpha. Because P alpha is EP P vector dot EQ minus Q vector. That is what this is. So this is EP EQ minus P dot Q. But if you write this is EP minus P dot EQQ. This is also EP EQ minus P dot Q. So when I am taking dot product of two vectors, where I put the upper index, where I put the lower index is irrelevant. So you don't have to worry about it. But important rule is, in a dot I cannot write P alpha Q alpha or P alpha. These are not defined. So in the dot product, one index should be up and one index should be down.
In this neutral current Hamiltonian you wrote, what are those G's? G, B?
So neutral current Hamiltonian arises because of Z0 exchange between the neutrino and the nucleus. Nucleus consists of protons and neutrons, and I am assuming that the protons, the neutrino interacts either with a proton or either with a neutron. It will not interact with both proton and neutron simultaneously. So only one of these two is important. But I consider both possibilities. And the Z mass is very close to W mass. So I expect the factor in front to be GF. There will be differences. The differences I take into account by introducing these unknown factors. The vector coupling of proton to Z0, axial vector coupling of proton to Z0, vector coupling of neutron to Z0, axial vector coupling of neutron to Z0. So I introduce these four, as of now, unknown couplings in writing this effective interaction. One way to do it is I do experiments and explicitly measure these things. That is, of course, the prescribed way. But I can also say that, okay, electroweak theory tells me what is the interaction between proton and the up quark is, not proton and up quark, between the neutrino and the up quark, and tells me the interaction between neutrino and down quark. And I think of proton as an incoherent combination of two up quarks and a down quark, and use the electroweak theory to calculate what this vector coupling of proton to Z0 is and axial vector coupling of proton to Z0 is. And for example, if you remember when we talked about matter effects, I talked about a potential which arises due to neutral current scattering. So that is what people do. That the neutral current, the potential due to neutral current scattering they calculate by taking the nucleus to be some kind of incoherent combination of the quarks, and use the electroweak theory to calculate the vector coupling of proton to Z0 and axial vector coupling of proton to Z0, and similarly for neutrons.
So here if the mass of Z0 was same as that of W, these couplings would be identical?
No, because they will not be identical, because the couplings of Z0 are more complicated. There is a sine square theta W which comes in the couplings of Z0. See, the W plus and W minus, they are directly the representations of SU2. But Z0 is a linear combination of W3 and the B meson, or rather that B gauge boson, and the B gauge boson is part of the U1 of the electroweak theory. And the U1 couplings are more complicated. And so those complications will enter into the Z0 couplings. So in general, this GB, GPV, GPA, GNV, GNA, if I write down their expressions, they look a little complicated, but you can be sure that they are numbers of order 1. So in that sense, this is not so different from this.
Just one related question.
Yeah.
So this mass of Z boson and W boson,
Mm.
they being close to each other, is there a reason behind it? I mean, are these masses input to the standard model? I mean, or is it specified by the standard?
No, the standard model makes a prediction that mw square is mz square cos square theta w. That's a prediction of electroweak model. And where cos square theta w comes from the ratios of the SU2 coupling and U1 coupling.
And standard model also predicts the GVP, those values also.
Huh.
Electroweak theory.
Yeah. So if I write it in this form, but there is a catch there. The catch is I have the prediction if I think of proton as a incoherent superposition of two up and one down quark. Somebody can question that. But standard model tells the coupling of Z0 to up quark and Z0 to down quark. And if I think of proton as an incoherent superposition of two up quarks and a down quark, then standard model predicts what this and this are. But in principle, one can question that assumption, that is proton really an incoherent superposition of two up quarks and a down quark. So anyway, that's what I want to say about the quasi-elastic or elastic scatterings. That based on Fermi theory or V minus A theory and electroweak model, we know the interaction Hamiltonian, and from that interaction Hamiltonian we can calculate the cross sections. Now, resonance scattering is actually one of the big headaches, so to speak. Actually, in principle, one can say that why can't I use the V minus A Hamiltonian? Because, for example, we have in quasi-elastic scattering, we have mu mu plus P going into, or rather, mu mu. This is quasi-elastic scattering, and I can write down a corresponding resonance scattering. And the delta plus decays into either P plus pi naught or N plus pi plus. So I take the V minus A Hamiltonian and say that, oh, I'll put mu minus psi bar mu gamma alpha 1 minus psi mu 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 times delta plus psi bar p gamma alpha 1 minus gamma 5 psi n given the Hamiltonian. I can formally write, and I know how to compute this. Question is, how do I compute this matrix element? How do I compute the probability that the proton absorbs enough energy? How do I compute the probability that the nucleon absorbs enough energy to excite the delta press resonance? And of course, people have been making models about it and trying to do those calculations. But any model, however sensible it is, it has to be compared with experiment and you have to validate it. And that is where a lot of effort is going on. And when you look at these models, people talk about one particle, one hole excitation, two particle, two hole excitations, ... So it's something quite complicated, and people have been, in fact, the very first papers on this were written in 1979, and over the past 45 years, people have been working on these continuously and refining things. And to the best of my knowledge, there is some reasonable agreement, but I don't think anybody can claim that, oh, I can exactly calculate all the resonance processes properly. So I believe resonances related to deltas people know how to handle, but handling the higher resonances is a tricky matter. So I will leave it at that, and we will now start talking about deep inelastic scattering. Now, the thing with deep inelastic scattering is, in order to appreciate it, we need to learn a whole new language, and I will introduce the language in today's class, and we will proceed in the next class. First, what is the first scattering experiment that you know of? Rutherford scattering. At least that is the first scattering experiment that I know of. I mean, of course, I don't know. It's possible that people talked about scattering before, but this is where, at least to my knowledge, where one tried to understand the inner workings of an atom through means of scattering. That you have a target and you throw things at it, and observing the pattern of how what you have thrown come out after interacting with the target, you try to figure out what the target is made of. So that is essence of scattering. And by the way, Rutherford's original analysis, this is a little bit of history. Who did the Rutherford scattering experiment? Answer obviously is not Rutherford, though it was done in his lab, and I believe on his suggestion. You know, I'm sure you have heard the name Geiger, of the Geiger-Müller fame. He was a postdoc in Rutherford's lab, and one young student joined Rutherford's lab, and Rutherford and Geiger were talking about what this young student should do. And I believe in the course of the talk, it was decided that they will do this scattering of alpha particles on a gold foil. And of course, the really great thing about the Rutherford scattering experiment, so here you have the gold foil target, and here you have the so here you have the radioactive source, and so any emitted particles, they can come out only through this direction and hit the gold foil. And it's natural to put a screen here. And what is the most amazing thing about Rutherford scattering experiment?
This side.
There are some 1 in 10,000 alpha particles came back. But how did they know that 1 in 10,000 alpha particles came back? That is because they put a detector here also, okay, with a hole in it so that the alpha particle can go through. And really one has to sort of salute the person who decided to put the detector here also. You can say, oh, what's the likelihood? What's the point in wasting a detector by putting it there? So this is the sort of importance in having imagination, number one, and doing a careful experiment, number two. So I believe the actual experiment was done by a young man called Marsden under the guidance of Geiger. One doesn't hear the name of Marsden in any other context. I don't know what he did later on. But, I mean, at least I won't mind the fact that Rutherford gets all the credit, because it is Rutherford, number one, who realized what the data meant, and number two, he did develop the mathematical apparatus and showed that this hypothesis of a massive positively charged nucleus at the center of the atom, that quantitatively explains the angular dependence that Geiger and Marsden saw. But Rutherford's first analysis was based purely on, this was in 1910 or 1911, there was no quantum mechanics at that time. His analysis was based on classical physics, but in 1926, after quantum mechanics, Born developed the quantum theory of scattering, and if you redo Rutherford and scattering using quantum theory of scattering, you get exactly the same answer. So there's no problem. And the Rutherford scattering, it is what we call elastic scattering. And so you have a projectile P hitting a target T, going into projectile P of energy E hitting a target, and comes out as exactly the same projectile P with exactly same energy as before. But there's a little bit of problem in the sense that by energy conservation this looks okay, but how about momentum conservation? Initially the projectile has a momentum in the z direction, target is at rest initially and target is at rest finally also. But after scattering, the projectile is going off in a different direction. It's not along z direction anymore. So there seems to be an apparent momentum conservation violation, but that need not bother us. The answer is that the target is many times more massive than the projectile. So we think of the target as a source or sink of momentum. Its situation is very similar to, there's a wall and I throw a ball at it. The ball bounces back with the same energy but with different momentum, and the wall is at rest before I throw the ball, it is at rest after I throw the ball. Does it mean that momentum conservation is violated? No. The reason is that we think of the ball to be so massive that it can absorb some finite momentum and not change its energy, or the change in energy of the wall is so minute that it's not visible. So that is the picture one has here, that the initial projectile and final projectile, they have the same energy. Initial target and final target have the same energy, so energies don't change. But how about momentum conservation? Well, we say the target is so massive that it acts as a source or a sink of momentum, so that even though there is an apparent momentum conservation violation. Actually, there isn't. That is the picture one uses in Rutherford scattering, and also that is the picture one uses when you scatter an electron of a proton. This is true even when you scatter a relativistic electron of a proton. That is called Molar scattering. Or actually, instead of proton, in general, we say a nucleus. But it can be proton also. That nucleus can be hydrogen nucleus, so it's just a proton. And Molar scattering actually is one of the highlights because Dirac proposed his theory of relativistic electron, which was a great success because we had Schrodinger's equation, but in order to explain a lot of features seen in atomic physics in Schrodinger's equation, one had to add a lot of perturbing Hamiltonians, the so-called relativistic correction, and then one had to add the spin-orbit interaction and various other extra corrections. And Dirac equation in one shot could explain a large number of those corrections. So that was one big success of Dirac equation. But this Molar scattering is another big success because you take a relativistic electron. Electron in an atom is not really relativistic. V by C is about a little less than 1%. But you take an electron with energy of a few MeV, so that it has a gamma factor of 10 or so. So it's a really relativistic electron. And you scatter it off a nucleus, and then you compute the dynamics of such an electron using Dirac theory, and you have again a perfect match between theory and experiment. So this is the Molar scattering is one of the early successes which helped establish the Dirac equation. But now let's consider Molar scattering, where you have here the nucleus is thousands of times more massive than the electron. So if the electron has energies of a few MeV, even if some of it is passed on to the nucleus, you can't really see it. But that is not the case here. So this will be for Molar scattering, the general process will look like this. And energy momentum conservation says that E1 plus E2 should be equal to E3 plus E4. So you now begin to see that we have to sort of modify our definition of what is an elastic scattering. The reason being, previously we used the definition of elastic scattering that final energy of the projectile is same as initial energy of the projectile. But that definition is too restrictive. So we need to develop a slightly more general definition of what an elastic scattering is. So in order to do so, and Molar scattering, actually I mentioned it just to illustrate that that old definition does not work so well, but in order to illustrate these issues clearly, the best thing is actually to use electron-proton scattering only. So initially there is a proton sitting at rest, and I shoot an electron at it with energy E1, and I observe an electron of energy E2. I am not observing the proton. So this is how I define my scattering process. I specify my initial state exactly. Proton at rest is my target, and I hit it with an electron of well-known energy, and I build my detector which is capable of detecting electrons very accurately, and I observe the final state electron with energy E2. In given these measurements, how do I define what is an elastic process and what is an inelastic process? So that is how I pose the question. So let me be more specific. This initial particles or initial momenta or K1 alpha or T1 or other Let me be a little more pedantic. So it has some energy E2, which in general is different from E1, and has a momentum K2. Now, my initial state defines a z-axis, but there is no way I can define an x-axis purely through my initial state. And this momentum K2, all I can say is that it makes an angle theta with respect to z-axis. So, without loss of generality, I will write this as the sort of initial data that is given to me is K1, and which implies E1 is root K1 square plus ME square. And final data that I measure are K2 and theta. And if I measure K2, of course, then E2 is root of K2 square plus E square. I look at only the electron, the final state electron, and I want to make a statement whether the scattering that has taken place is an elastic scattering or an inelastic scattering. So let us try to address this question. Let us define Q, which is the momentum transfer. So that is the momentum transferred from electron to proton, or equivalently it is the momentum lost by the electron. So by definition it is K1 minus K2. Which is of course the momentum gained by proton. And let us compute Q square, which is Q alpha, Q alpha. This is K1 square plus K2 square minus 2K1 dot. k1 square is the 4 vector momentum square of an electron in the lab. So by definition it has to be ma square. And same is true for k2. So this is 2ma square minus 2 E1 into minus k1 k2 cos theta. And this is approximately minus 4 E1 E2 sin square theta by 2 if k1 k2. So note that this q square is negative. And in general, the q square depends both on theta 2 and theta, on E2 and theta. And now, as I kept emphasizing, I am only observing the final state electron. I am not looking at anything else. It's true I am not looking at anything else, but I'll start making assumptions about the final state excluding the electron. So what is the simplest possibility for the final state if I exclude the electron? No, it can't be at rest. I mean, there is some momentum transfer that has taken place. So the proton remains a proton. It's a physical proton in the lab. I don't see it, but it's a physical proton in the lab. Which means that the P2 EP, Q, this is the, rather, first let me write the assumption explicitly. Suppose final state is electron with E2K2 plus proton with EPQ. Oh. Suppose the final state is a 2-particle final state. It means that EP square minus Q square is equal to MP square. It's a physical proton, and physical proton has to satisfy the on-Marshall condition. But I can find out what EP is from the energy conservation. EP is equal to E1 plus NP minus E2. So I will write this as MP times just I define Y is equal to 1 minus E2 by E1. No, okay. Yeah. This is MP plus E1 times 1 minus E2 by E1. This is MP plus E1 times Y. So I have introduced a dimensionless parameter Y. So now I substitute things in this equation. So I have MP plus E1Y whole square is equal to Q square, which is let me assume that I am in the my electrons are ultra relativistic, so I can make that approximation. Minus 4 E1 E2, or I'll write Q square is equal to Q square plus MP square. So I have MP square plus 2 MP E1Y plus E1 square Y square is equal to Q square plus MP square. So the MP square cancels out, and I have and I divide throughout by this factor. If I do that, I get 1 plus E1Y by 2MP is equal to Q squared by 2MP E1Y. if I take it to this side, I hope I have not made any sign mistakes. Let me just check. Yeah, EP minus Q square is equal to MP square. I have made a mistake. The mistake I made is this is whereas later I substituted the 4 vector Q squared. So that was the mistake I made, because the final formula was not coming out correct, and that's how I caught that I made the mistake. This Q is the 3 vector momentum of the proton. So I should substitute, and this is correct. Total initial energy minus E2, so that is correct. But here I have to this is where I made a mistake. So mod Q vector square is mod K1 minus K2 mod square. So this is K1 square plus K2 square. K1, again let me put mod squares here, so that that's 2 mod K1 mod K2 cos theta. Fine. And I am assuming my initial and final electrons are ultra relativistic. So mod K1 square is E1 square and mod K2 square is E2 square. So this is E1 square plus E2 square minus 2 E1 E2 cos theta. This is E1 minus E2 whole square. So times plus 4 E1 E2 sine square theta by 2. I subtract and add to E1 E2. So subtraction converts this into this, and this becomes this, and so from that we see that this is EP minus MP whole square, and this is minus Q square. Fine. Where this is the 4 vector product. So is that fine? So now I have EP square minus MP square is mod Q square. This is EP minus MP whole square minus Q square. So if I write this, EP square minus MP square is equal to EP square minus 2 EP MP plus MP square minus Q square. So this EP square cancels out and I have 2 MP times EP minus MP. So I bring it to this side and MP square also I bring to this side is equal to minus Q square. And you see that EP minus MP is E1 minus E2. So I have 2 MP E1 minus E2 is minus Q square, and remember Q square is negative, so right hand side is positive. So you see that what is given to me, the initial energy of the electron E1 is given to me, and the final electron, the state of the final electron, the kinematics of the final electron I measure, its momentum and the direction of the momentum. As two independent variables, I measure that. But if the final state consists of two particles, then between those two kinematical variables describing the final state electron, there is this constraint. Remember, Q square is a function of E1, E2 and theta, and right hand side has E1, E2. So this equation is expressing a constraint between E2 and theta. So I don't have to see what is happening to the proton. I just see the final state electron. I measure its momentum, I measure its direction of that momentum, and ask the question, do those two variables satisfy this equation? If they satisfy this equation, I know without looking that the proton has remained a proton. Whereas if this equation is not satisfied, then I know that something has happened to the proton, and whether a resonance got excited and the proton broke up into a neutron and a pion, or something else even more serious happened, I don't know. All I look for is this equation satisfied or not? So, and we define a variable called x. call it elastic scattering, whereas and if x is noticeably less than 1, like 0.5, 0.3, then we say it is deep inelastic. X has a kinematical range 0 to 1. So for values of x less than 0.5, we say that we are in deep inelastic range. So people have been doing scattering of electrons, of nuclei, and of protons, I guess ever since people managed to build electron beams. And there was a famous Hofstadter experiment in late 50s or early 60s, which showed somewhat what is called scaling behavior. What scaling behavior is, I will describe in the next class, which showed that if you scatter an electron of a nucleus, the electron actually is sensitive to the distribution of protons and neutrons in the nucleus. When we study nuclear physics, we spend a lot of effort in trying to understand how the quantum mechanics sort of forms through quantum mechanics, how protons and neutrons combine to form nuclei. We worry about the Fermi statistics, we worry about the shell model and how the protons and neutrons fill the shells according to the quantum rules, etc., etc. But what Hofstadter experiment showed is that once you go to and all these are important when you are talking about energy scales of MeVs or tens of MeV. But when you do scattering experiments on nuclei with electrons of energies 100 MeV or so, or maybe 200 MeV, remember the de Broglie wavelength of 100 MeV is about 1 Fermi. That's how Yukawa estimated the size of the pion mass. So if you do experiments with electrons of such energies, you are sensitive to the substructure of the nucleus, and when you are sensitive to the substructure of the nucleus, this so-called scaling argument shows that the electron is not scattering off the nucleus, but it is scattering off a subcomponent of the nucleus. It is scattering off a single proton in the nucleus. So, Hofstadter did this scattering of electrons of hundreds of MeV of various nuclei, and he could show based on his scaling arguments that if he took carbon nucleus, the electron is seeing 6 protons. If he took a nitrogen nucleus, the electron is seeing 7 protons. If he took oxygen nucleus, the electron is seeing 8 protons, etc. And 10 years later, experiments at SLAC went up one order of magnitude. They shot electrons of energies of a few GeV of proton, and they saw a scaling behavior. And that scaling behavior originally was very puzzling. And Burekin, he came up with slightly complicated explanation as to why that scaling is occurring based on the currently popular field theory, which went under the name current algebra. But in 1972, Feynman came up with what is called Proton model, which essentially expanded the picture that Hofstadter used to show that the scattering of electrons of nuclei appears to be incoherent scattering of electrons of the component protons of the nucleus. So Feynman made exactly the same argument, that the deep inelastic scattering data that was obtained at SLAC can be explained very simply by assuming that the electron is scattering of point-like components of proton. That is called the Proton model, and I will discuss how that. First, I will briefly discuss about how to do the parameterization of the scattering data and how Feynman came up with the Proton model. By the way, if you have a chance, it's not the best reference, but I prescribe it because I learned it from this book. Read section 7.1 of Cheng and Lee. It's not easy to understand, but at least read it so that you are familiar. I will try to explain the physics in better language compared to what Cheng and Lee have written, but you will be familiar with the language that I will use, and that will help a lot. So yeah, so all of our discussion is going to depend on this quantity x. By the way, in x, numerator is defined in terms of a Lorentz invariant quantity, but the denominator is not. But you can trivially see that I can write the denominator as x is a Lorentz invariant quantity where p is the initial proton momentum, proton 4 momentum. So p is mp0 and q is e1 minus e2. So it's trivial to see that the denominator is 2p dot q. So we have a definition of x in terms of Lorentz invariant quantities, and this variable is going to play the starring role in what we are going to discuss in the next 2-3 classes. Okay, I'll stop here now.
In this deep inelastic scattering,
Yeah.
Inside a nucleon, do the quark, do the gluons play any role? Is steady scattering of gluons?
Not with electrons, of course, because gluons are chargeless. And so if you are talking about deep inelastic scattering of electrons or neutrinos, answer is no. But they play an indirect role. We will definitely discuss that. There is something called a momentum sum rule. And the momentum sum rule, when you do the measurement of momentum sum rule using electrons, you expect an answer 1 if all the partons are charged particles. But experimentally, measurement gives a number half, which means that half the particles are not charged. And if you combine that with the QCD, you say, okay, half the charged partons are quarks and the uncharged partons are gluons. That's an interpretation, but that is the interpretation people use in doing all the simulations of LHC.
So electrons, neutrinos, they don't scatter off the gluons. So
yeah, but
some other.
I mean, if you use if your projectile is a strongly interacting particle, then yes.
This momentum fraction you're saying.
Yeah, we'll discuss that. I mean, I have to build up the structure. I have to, unless I build up the language, that momentum sum rule, it will not make sense.
Here we said Q square is negative.
Yeah.
So that implies Q to be imaginary.
No. This is 4 momentum square. So Q square, I mean, I'm calling it Q square, but it is Q0 square minus Q vector square. So Q0 is a real number, Q vector, each component are real numbers. Or what I'm saying is the Q square is space-like. The momentum transfer can be, in some cases it is time-like and in some cases it is space-like. But in deep inelastic scattering, it is always space-like.